So we are moving along with what we've been doing for a little bit. We're looking at, we're starting a new chapter. We're entering a new stage where we're beginning to get into multivariable functions and their limits. So first off, when we talk about a multivariable function, what we're talking about is a function of two variables that assigns some number z to every pair of numbers x and y from some subset of the real plane, which we're calling R2, and that subset is usually denoted by D. D is the domain of F. It's basically, the only real way you can think about this is by doing examples with it. So here are a couple examples. You can look at Fxy as defined by the square root of x plus y plus 1 over x minus 1. And that, let's think about what the domain of that thing is. That domain, well, clearly x can't be 1, because if x were 1 for this function, and we can see that right here, if x were 1, then we would have this issue with x minus 1 in the denominator, and then if we have our xy axes, x plus y plus 1 is greater than or equal to 0, or in other words, y is greater than or equal to negative x minus 1. So in other words, here's negative 1, and here's the line y equals negative x minus 1. So, and meanwhile, we also have to have that x cannot be 1. So our domain in this case is this entire region. It's everything that's below, I'm sorry, not below, above. My mistake. It's everything that's above this plane, but not including this line, x equals 1. So that's the domain of that function. That would be D in that case. So now meanwhile, you can evaluate this. You can say, for example, f of 3, 2. Well, you just plug in 3 and 2 for x and y respectively. And you do that calculation, you end up with f of 3, 2 equals 1/2 root 6. We can also talk about g ln y. G ln y is another has to be positive. So what does that domain look like? That domain looks something like this. Y squared is greater than x. X equals y squared is this sideways parabola. And in this case, what we actually have, it would really, let me actually do that differently and make it this dashed parabola. And the reason I'm making it dashed is because it can't actually include that parabola, because ln can't actually be 0. But y squared is greater than x, so that's just everything above it. That's the domain of that function. So, we can do this a little bit. We can see what these different things look like, et cetera, et cetera. So that's great. Wait a second. Okay, so moving right along. Uh-oh, lost my place. Moving right along. So now these actually appear in nature all the time and in science and engineering all the time. For example, we can look at what's called the wind chill index, which is, we don't experience this right now, perhaps because it's beginning to be summer, but the wind chill index is known as the Cobb-Douglas production function. So in this case, you can talk about the total production of a nation's economy, and that's modeled by the function PLK, is BL to the alpha times K to the 1 minus alpha. In this case, B and alpha are two constants depending on the nation, the product in question, etc. L is the amount of labor, and K is the capital that's invested. We call this the Cobb-Douglas production function. Okay, so Now, if we think back to how we visualize single variable functions fx, we visualize them using graphs. These are curves in the plane, all of whose points satisfy the equation y equals fx. A similar principle exists for functions of two variables. In that case, it's the surface in R3 with the equation z equals f of x, y. It's pretty much the exact same principle that we saw before. So, for example, you can look at the graph of the function fxy equals 6 minus 3x minus 2y. That's a function. It's a perfectly reasonable function to look at. The graph satisfies equation. And what is that? Can we see what that is? What does a surface look like whose equation is 3x plus 2y plus z equals 6? Think about that for a second. And after a moment, we realize, oh, that is going to have to be a plane. That's a plane, right? So every point that lives on that graph lives on that plane. So the graph is a plane, in fact. So what about the graph gxy equals the square root of 9 minus x squared minus y squared? Well, again, you can look at the surface, and the corresponding surface has the equation z equals root 9 minus x squared minus y squared. Squaring both sides, of course, gives you z squared equals 9 minus x squared minus y squared, and you move those over, and you get x squared plus y squared plus z squared equals 9. Now, that's a surface we're all familiar with. But there's a trick here, that there's something we have to be a little bit careful about. That's our up here, that's only a positive square root. The function is only determined in terms of positive square roots. The domain, meanwhile, is going to be d equals, you can write this as all x and y, so that x squared plus y squared has to be less than or equal to 9. That's about the best we can do. And that makes sense, because if x squared plus y squared is bigger than 9, then you're taking the square root of a negative number, and you're in the complex numbers, and we're not going to go there. Now, I want to return to this point about this graph as a half sphere. There is a vertical line test for multivariable functions. Any vertical line can only intersect the graph of multivariable function in at most one point. And if you think about circles, if you think about what circles look like, circles, when we're graphing those things, that's a circle. But the vertical line test, you do the vertical line, drop a vertical line down there, and it intersects at 2 different points. So it fails the vertical line test. Spheres also fail the vertical line test, and in the very simple sphere, because it can only return one point. You can only have one point along a vertical line that goes to the graph. Okay. Now, how do we analyze these things? Well, the bad news is that graphs of two variable functions can be very difficult to draw by hand. Typically, we have computers do this for us. That being said, we can understand graphs a little more conceptually and kind of get a better sense of what they look like by using what are called level curves. Now, level curves, these are curves of a function that when projected into the xy plane are of the form fxy equals k for some constant value of k. Really what this is, it's a topographic map of the function's graph. So look at this figure, this sort of sombrero-looking thing on the left-hand side. And you notice that along each of these curves, or along each of these horizontal slices through this graph, that projects down to a different curve in the xy plane. The same thing is going on in a topographic map on the right. So on the right, all of those curves phenomenon is going on with the topographic map of this level curve, or of that surface rather. So let's consider the following set of level curves. We can look at that and try to get a good sense of what's going on with this function at that point. F of 1, 3. What's going on at the point f of 1, 3? Well, at 1, 3, where are we? X is going to be 1, so here we are at the point 1, and we're going up to 3, so we're over here at this point over here. So looking at what's going on at this point, that's about between 70 and 80. I'm going to approximate that and say that's probably about 72, maybe 73. So that's right up there between 70 and 80, definitely more on the 70 side than the 80 side. What about 4, 5? Well, the point 4, 5 is right up here. Actually, I'm going to do that in a different color to make it stand out a bit more. Here's the point. That's basically it with how these level curves work. That's pretty much the entire story. So let's look back at the graphs that we had before. So for the plane, we had fxy equals 6 minus 3x minus 2y. Now the level curves of that thing look like 6 minus 3x minus 2y equals k. K are different constants. And if you actually undo all that, then you get y equals negative 3/2 x plus 3 minus 1/2 k. Now again, k is a constant. That's very important here. So if k is a constant, we can see what these curves are. Those curves are going to be actually parallel lines. Uh-oh, trying to draw this. Yes, those curves are parallel lines for different values of k. And they're showing you the elevation. Do I have this on the next thing? No, I don't. Okay. But the gist basically here, and what we're looking at is on this curve, it's going to look something like this, where we've got these different level curves, all of slope negative 3/2 x, but they're all parallel. So we've got all of these parallel lines, and they're evenly spaced. These are our level curves, and perhaps this is, and I don't know, maybe this is going to be 0, -1, -2, or actually no, probably more likely would be 1, 2, 0, -1, etc. So what we're seeing here, in other words, the plane in question would be rising up out of the screen, out of this slide, and we would see that going in the sort of rising up in the, I suppose, the southwesterly direction from our perspective. So what about the graph gxy equals root 9 minus x squared minus y squared? Those curves are going to be of the form x squared plus y squared equals 9 minus k squared. And those, if you think about what those are for a second, those are concentric circles. Those are going to be concentric circles, and their radius, the radii of these circles, and 0 well, then we're not in the function's range anymore, are we? Because at that point, you know, we can see that this function can only be positive, or at least non-negative. So the smallest thing that k can be is 0. The biggest thing that k can be is 3. And these curves are going to form these sort of concentric circles. Right. So, which would look something like this. Perhaps here's the radius 3, and then perhaps here's a radius of 2. And then over here is a radius of 1. And meanwhile, the actual, I'm going to try and make it a little less lumpy looking. Meanwhile, the actual surface in question is this sphere. So what we're seeing here is that these level curves correspond to these horizontal slices through that surface, through that half sphere. Of k. And in other words, that means 4x squared plus y squared equals k minus 1. Now we know what those are. Let's think about that for a little bit. You've got 4x squared plus y squared. Those are two square terms. They're both positive. They're equal to some constant. We know back from chapter 12 that these are ellipses. But they're only ellipses for values of k that are greater than 1. Greater than 1. Otherwise, you would have that the radius, or whatever that constant is on the right-hand side, would be negative. And if it were negative, then you'd have the sum of two positive things. That can't possibly equal negative things, so that's not going to work. Now, what about the graph? The graph satisfies 4x squared plus y squared plus 1 equals z. And again, we recognize this from chapter 12 as an elliptic paraboloid. Okay, so that's what these graphs actually look like. Ellipses. Notice, by the way, that the ellipses get a little bit more tightly packed together the higher up they go. And that has to do with the steepness. Right? The steeper these level curves are, or the steeper the function is, the tighter the level curves are going to be, which makes sense. As the, if the rate of change of this thing is increasing, then you're going to have to go shorter distance to get higher up. Just like in topographic maps for mountaineers. By the way, in this case, we have a graph of the form, or a graph of a function of the form ax squared plus by squared plus c. That's a quadric surface. And if we want to think about the level curves of that thing, we recognize what those are from chapter 12. Those level curves are no more, no less than the traces of the quadric surface that we looked at in chapter 12. So what do we notice about these level curves? Well, some general observations we can make is, like I said before, circles or points are usually going to be peaks and valleys. Not always, but essentially, well, no, always. Circles and points are if you look at the first of these things, the first of these examples, you've got four of these dots, four of these sort of centers of whatever, and you notice that those correspond to two peaks and two valleys in the actual function, which is to the right. Same thing is going on for these two peaks, for this one peak and this one valley in the lower function. Now that's one important observation. The other important observation is that if the, as I already mentioned this, but when the curves are more tightly packed together, that usually indicates that the function is much steeper in those areas. Again, both of these phenomena you see in actual topographic maps. Now, there's nothing to say that you have to talk about only two variable functions. We can, in fact, we will talk about three variable functions also. In fact, you can talk about any number of variables in a function that you want. The problem is these get harder and harder to visualize. Even just going to three-dimensional functions, you've got to go into four-dimensional space to visualize what that graph looks like. So that's going to be kind of freaky and weird. Of fxyz, in this case for different values of k. So you can, for example, consider the function fxyz equals x squared plus y squared plus z squared. That's a legitimate function. That's a perfectly legitimate three-variable function. There's nothing wrong with it. If you set it to a constant, you get a sphere. That's the power of this thing, is that for setting this to constant values, you're going to get a sphere. Or several spheres that are all concentric, much like the example we saw before with x squared plus y squared, or 4x squared plus y squared. Now that's basically the nuts and bolts of what multivariable functions actually are. But this is a calculus course, and as soon as you talk about multivariable functions, we need to have some way of talking about continuous multivariable functions. And for that matter, we have to define what continuous actually means. And if we're going to talk about continuity of multivariable functions, we necessarily have to talk about limits. So we're going to write down the following definition. The limit of xy going to ab of f of xy goes to L, but that's and you can look at that in another way. You can say fxy approaches L. That's what the little arrow means, as xy approaches AB. And again, really all that we're saying here is that this output of this function gets closer and closer to L as your input gets closer and closer to AB. That's all that this means. Now, it's not very rigorous. It's not very technical to put it that way. And there is a more rigorous definition that we mathematicians use sort of as the industry standard, known as the epsilon delta definition. But we're not really going to use it too much in this course. It's a little rigid for what we want to do. But if you're curious, then it's definition 1 on page 944. But and I leave it up to you to look that up if you so wish. Now, that's basically the same thing that we saw in Calc 1. Now, a better question to ask is, when does it not exist? When does a limit not exist? Well, there are really two ways that this can happen, that they're kind of similar in some respects. The first thing that can happen is you could have that the function fx blows up at this point. And one example of this is the function And what happens with the limit? Well, if you're going down the right-hand side, that's just x over x, and that's 1. But on the left-hand side, that's negative x over x, because we're looking at absolute values, and the next would be negative, and that would be negative 1. So in that case, the limit doesn't exist. It doesn't blow up, but it doesn't exist either. It's a discontinuity of the system. Now, the same principle applies to two variable functions. In particular, this limit does not exist if fxy approaches different numbers as xy goes to the point AB along different paths. Now, here's the issue with this. In one variable calculus, in single variable calculus, you really only have to worry about two directions. Namely, you could be approaching your limiting point from either the left side or from the right side. But that's not going to happen for two variable functions. For two variable functions, there are infinitely many paths that you can take to get to AB, which is weird, but that's what happens. So, let's look at some examples about what can go wrong here. Well, looks like. So here are our axes. Now you could go along, no, on the one hand, you could go along the x-axis. So xy goes to 0, 0 along the x-axis. That means we're approaching in this direction, going to 0, 0 that way. The problem is, and if we're doing that, then that means that y is 0. Y is always going to be 0 along that path. So you plug in y equals 0 along that path, because that's the behavior along that path. Y equals 0, x squared over x squared, that's just 1. But what about the y-axis? What if we try approaching this that point along the y-axis? What happens then? Again, you go along the y-axis, and now in this case, you have that x equals 0, but along x equals 0, you plug in x equals 0, you get the limit as y approaches 0 of negative y squared over y squared. That's negative 1. The upshot of all of this is that we now have two something on GeoGebra that I should have done before, so please bear with me. Now, if we actually look at this function in GeoGebra, what was that function? It was fxy equals x squared minus y squared over, oh, no, sorry. No, that's not what I wanted to do either. Let me try that again. fxy equals x squared plus y squared over x squared minus y squared. And what do we notice happens? Well, along the line y equals x, sorry, excuse me, along, did I type that incorrectly? Wait a second. I think that I may have, no, I think that I put my signs backwards. Let me try that again. X minus y. As you go to 0. But if you go along the y-axis, you hit negative 1. So this function approaches two different things. Even though it's nice and smooth and continuous everywhere else, it pinches horribly at the origin. So that's what's going on with this very strange function in this case. Okay. So now now what about, here's a different function. You could have the function fxy over is equal to xy over x squared plus y squared. Now, does this limit exist? Well, along the y-axis we get 0, and along the x-axis we get 0. So far this looks promising, right? So in other words, if you are going along your axes and you go along the x-axis, which I'll do in red in keeping with what GeoGebra. You get 0, so that's fine. Along the x-axis, on the other hand, then that's also 0. That's good. But what about the line x equals y? Now let's go along the line x equals y. I'll do this one in purple. So along the line x equals y, we're going along a different path now. But along the line x equals y, something very strange is going to happen. Along that path, we get x squared over x squared plus x squared, right? Because then x equals y, that's 1/2. So there it, again, looks kind of different. So along that path, it still doesn't exist. So again, let's, 1 second. So let's consider what that function looks like. It's like fxy equals xy over x squared plus y squared. Doesn't like that. Let me try that again. So in this case, along the, let me try zooming in a little bit so you can see the weirdness. Along the x-axis, it's 0, and it's also 0 along the y-axis, but along the line x equals y, it's 1/2. So it's basically, it's still pretty similar to the weird thing we saw last time, just rotated and condensed. But it's the same issue. You go along different paths, you get different results, and it's still not good. So still, we don't have a nice graph at that point. It's still, the limit still doesn't exist there. Now, I don't want to have to check every single path individually. So is there a way that we can check all linear paths at once? Is there a way to just knock out all lines at the same time? Well, yeah, there is. If you're looking at paths to the origin, they're either going to be of the form y equals mx or x equals 0. So in other words, if that limit exists, it has to be the same along every path, regardless of what m is. So let's look at a previous example. In our previous example, we had fxy equals xy over x squared and you plug in mx4y, you get mx squared over x squared plus m squared x squared. The x's cancel if you're not 0, and we're not 0 as we're approaching it. So that becomes m over 1 plus m squared. That's the limit. And the problem is that limit is going to change depending on the slope of the line we're approaching along. So for m equals 0, we're approaching along y equals 0. But for m equals 1, we're approaching along y equals x. And that's the limit 1/2 in that case. 1 over 1 plus 1, that's 1/2. So what that means is that for different slopes, we're going to get different numbers. And the limit does not exist in that case. So that's the issue that's going on over here. Okay. So now it's not a perfect, it's not a perfect system. So where can this go wrong? Well, let's look at the function xy squared over x squared plus y to the 4th. We'll start off along y equals mx, and what do we get? Well, again, you plug in y equals mx, you got the limit as x goes to 0 of m squared x cubed over plus 0 or 0. So with that, and by the way, along x equals 0, we're going to get the same thing. Along x equals 0, we get the same exact behavior. 0 over 0 plus y to the 4th, that's still 0. So what that tells us is if you go along any line through the origin, it's always going to be 0. Now here's the question. At this point, can we conclude that the limit does in fact equal 0? It's very tempting to say that the answer to this question is yes. It's very tempting to say, yeah, sure, of course it's 0 at this point. We just saw that it always goes to 0 no matter what line you go through. But we can't conclude that. It turns out that you need to check not lines, but entire paths. We only checked lines. There could be another path where it's something different. So what about the parabolic path? X equals y squared. Well, if you go along x equals y squared, then it becomes y to the 4th over y to the 4th plus y to the 4th, or 1/2. So along the parabola x equals y squared, you get something that's not 0. So the limit doesn't exist, even though So let's take a look at what this thing actually looks like. I'm just going through what we just saw. What was it? It was sorry. Let me delete and redo this. We can take fxy is equal to x. What was it? It was xy squared over x squared plus y to the 4th. Oh. And that's a funny looking thing, isn't it? But what do you notice? Well, you notice that if we're, let's really zoom in here. And if you really zoom in and you are going down the x-axis, say you're going down the x-axis and you get over this ridge, if you get over that ridge, then you just plummet right down very quickly to, you very quickly plummet down right to 0. Or to put it another way, you're always starting at 0 in that case. If you go along any other line, you get around that ridge and then you start plummeting down to 0 very quickly. But if you go along the parabola itself, we can kind of see this in the shape of this graph. If you go along the parabola, let me try it again. Point is, the point is, as you go along this ridge, actually either ridge, you can do it with the negative, and you get the negative side of that as well, you end up with 1/2. It's weird. It's a weird function, but that is exactly the behavior we see. So the point here is that you can't just conclude that because it goes through every line and it's the same thing, that it's the same along every path. That's generally not true. So when the heck does this limit exist? Well, the good news is that most of the functions we'll be working with are going to be what we're going to call continuous. They're going to be continuous on their domains. And here's what that means. A function is continuous at the point AB if, first of all, the point AB is in the domain of your function, and second of all, the limit as xy approaches that point is actually equal to the value of f at that point. And what that means is that if a function is continuous at a point, then you can just plug in the number immediately. So take, for example, if you have fxy gives you 0 over 0, well, the limit may or may not exist. But you have to sort of figure out whether or not it does. And we'll look at how to deal with that in a little bit. But most functions we'll be working with are going to be continuous. That's the good news. So here are some continuous functions that we've seen before. Any polynomial in x and y is continuous. So for example, x squared minus y squared is continuous. xy minus x cubed plus 7x squared y cubed minus 4. That's also continuous. Any combination of x's and y's or powers or sums and products, that's all fine. That includes constants. Constants are continuous, and that's perhaps very easy to see. Of course, a constant function is going to be continuous. You move x and y a little bit, that's not going to change the constant. It's a constant. Rational functions are continuous as well, provided that qxy, the denominator, provided that the denominator is not 0. So rational functions are okay. Trig functions, log functions, exponentials, radicals, those are all continuous as well, provided you're on their domain. So for example, we already saw this. You can't be plugging in negative numbers under a radical, and you don't want to be plugging in 0 or negative numbers into a logarithm, etc. Easily. So for example, take the function fxy equals x squared y cubed minus x cubed y squared plus 3x plus 2y. That's a polynomial in x and y. That's continuous everywhere. So if you want to find out what the limit as xy goes to 1, 2 is, that's going to be x squared plus y cubed. Well, okay, I won't read it aloud. You just plug the numbers in and see what falls out. It's 11. That function is continuous. You can just plug that limit in. That's not a problem. What about the function gxy equals x squared? Sorry, let me try that again. The function gxy is 2xy plus 1 over x squared plus y squared. Now that function is not like I said. Now, what if you have 0 over 0? This is the instance that everyone really dreads. Well, very broadly speaking, if we Okay, I think I'm back. I was gone for a second. So the point is with this algebraic example, I don't know how long I'll last, so I'm going to try to get you can immediately just cancel the x squared plus y squared, like so, and that just gives you root x squared plus y squared plus 1, and that's a continuous function, so you can just plug in as xy goes to 0, 0. But this is a tricky one to algebraically manipulate. So we're going to try to find some other function, gxy, so that the absolute value of this thing is less than gxy, but that goes to 0. Okay. The upshot of all of this is that gxy equals 3 times absolute value of y. That will guarantee clearly as y goes to 0, 3 times absolute value of y is also going to 0. So by the squeeze theorem, we can see that that thing in the middle, the function we're interested in, is going to 0 as well. So that's about it. We know at that point, now we can say with certainty that 3x squared over x squared plus y squared is, in fact, going to 0. That's the end. Basically, we saw at this point that we need this function to have a limit at 0, 0. And 3x squared y over x squared plus y squared. That has a domain, everything except 0, 0. But now let's define a new function where we're going to plug that hole at 0, 0 with some other number c. So here's a question. For what values of c, if there are any values of c, one over x squared plus y squared plus z squared minus 1, that's continuous everywhere except on the sphere x squared plus y squared plus z squared equals 1. On that sphere, the entire function blows up, and it's not continuous anymore. It's not even defined. All right, so hopefully this was informative. Thank you, everyone. And I will continue this lecture. I will pick back up with multivariable functions and doing actual calculus with them tomorrow, and hope